Okay. So we have started the AP Chem exam review. I really was hoping that there would be questions, and I had planned on posting some questions. Unfortunately, I didn't get any listed. So hopefully you guys will bring some questions. I don't know if anybody got any up. Oh, good. See, I already got some up. So, so we'll talk about some of the questions, and I will just say questions. Unfortunately, I won't be able to go through and bookmark where all the things that I'm hoping to talk about, but that's okay. If we can fill this time with your questions, then I'll be happy with that. All right. So let's go ahead and just start with the question. Sierra's question is, select it. There we go. Will we have to be able to identify the state of a compound for the exam, the AP exam? If so, how do you suggest figuring this out? You most of the time will not. Sometimes they will tell you. But I will say this, that in the standard conditions, standard state conditions, room temperature, that is the only time that they would expect you to know what the state of matter is. And if you look at a periodic table, in fact, I want to see if I can find a periodic table. It'll be much easier to talk about. Most of them fall into just a few categories. Let's see if I can do one that has temperature states. Here we go. This actually will, oh no, it's a little bit smaller than I thought it was going to be. Let's see if we can get a bigger one. I'm sorry, this may take a little while. Well, not that long, actually. Let's try this one. That one's a good one. Okay, I'm going to share a picture with you now. Here we go. So when you are looking at the periodic table, most elements are going to be solids. Everything that you see there that's the green is a solid. There are only two elements that are liquid at room temperature, and that is mercury and bromine. And then everything that's in yellow is a gas. So you're looking at all the noble gases and half of Brinkelhoff, right? So you can see here the chlorine, fluorine, oxygen, nitrogen, and hydrogen. And now what I would say is this. The only piece of this that I think is very interesting, but that you would probably have to really work out, is the fact that the halogens are all three states. Fluorine, chlorine, bromine, and iodine. You cover all the states of matter. So why is that? If you're looking at this, fluorine and chlorine are very small. And so we're looking at intermolecular forces. They're diatomic, so they're non-polar, but they're small. And so it's just van der Waals forces, and they're not going to be very sticky. They're not going to push into each other. So they're going to stay as a gas. Once you get to bromine, it's still diatomic, it's still non-polar. However, the electron cloud surrounding the atoms is much larger, and so it's stickier, and you get an induced dipole. So now the element can stay stuck together for a little bit longer, meaning that the molecules, the bromine molecules, will actually be closer to a liquid. And then finally, iodine is very large. The electron cloud is ginormous, right? And so it really sticks together. It is induced dipole, gets a very large, it's very polarizable. And so you end up with a solid state for iodine. So this is the only thing that you would think about. And so I've just kind of walked you through this. Noble gases are all gases. Halogens are half gases, and then solid and liquid because of the size, the polarizability of the diatomic molecules. And basically the rest of it is solids, with the exception of mercury. You think about mercury, thermometers, or all the dangers of mercury floating around. The rest of it, you're going to probably be told more or less what it should be. You used to have to figure some of this out based upon the wording with the net ionic equations, but there's not very many of those. We didn't spend a lot of time on that, so I wouldn't worry about it. Hopefully that answers your questions here. So I'm going to click that as done, but please feel free to ask any further questions on that. My voice is already drying out. Okay, excuse me. So I was thinking that we would go back through, there's big idea 1, big idea 2, and then tomorrow we're going to start on big idea 3. And I totally messed this up. I said there were 5 big ideas. There's 6 big ideas. I kind of glossed over that last one, which is really important, which is the intermolecular bonds. But I believe is it big idea? I don't know. One of them is not as long, and maybe we've already done it. But anyhow, to make a long story short, I've combined the next tomorrow into big ideas. I think I've got big idea 3 and 4 together. We can take a look at it. But let's go ahead and start with big idea 1. And let's try to talk about the most important things for each one. I ask that you would please write down the questions, though, or type in questions, and that will help us out immensely. And it'll help your review a lot. So I'm going to go ahead and bring up the bamboo paper. Oh, look, we already have a question. Could you do number 45 on the practice examination number 2? Sure. And of course, I'll stop wherever I am. This is for you guys. So I want to make sure that you're getting your questions answered. So practice exam. So, okay, so that's the one we did. Oh, I should get the question out for me. I have paper spread out all over my floor from when you guys ask questions, so I can just reach down and grab it. All right. 45. Oh no. I seem to be missing that page. Oh, that's pretty clever. How did that happen? I have the book though. Practice exam 2, number 45. How did I miss that page? Okay, so I'm going to go ahead and type that up, and then I will get to the solution. All right. So this is, oh, I need a smaller, there we go. Practice exam number 2. And if I want to remind you guys, I would like to remind you guys that that's due by Friday. If you can get Thursday, it's a lot easier than having to track me down on Friday, but you have until Friday to complete that exam. So this is number 45, and it's got to be a multiple choice, obviously. So 45 has a reaction. Awkward, since I don't actually have the electronic version in front of me. So we have 2 SO2. Wow, so much for looking somewhere else. I looked down for a second, which I don't normally do. All right, number 45. Okay, so we have 2 SO2, which is a gas, plus O2 as a gas. Yield, oh, it's in equilibrium though, with 2 SO3 as a gas. And it has a K1. And they want to know what is the value of K for the reaction. And so then they just took it and they made it SO3 gas is in equilibrium with SO2 gas plus 1/2 O2 is a gas. Okay, but they want to know how that works. So I want you to notice 2 things. Number 1, okay, the first thing, they flipped the equation, or you could say they reversed it, okay? I've got to get my handwriting. I've got to slow down and make this better handwriting somehow. Which means that if you reverse the reaction, then for equilibrium, then on this problem, it becomes 1 over K1, okay? And then you'll notice that each of the coefficients have been divided by 2. So the 2 is divided by 2, and you get 1 for the SO3. The 2 SO2 is divided by 2, you get 1 SO2. The 1 for the O2 gets divided by 2, and you get 1/2. So if you remember that if you if you divide it by a number, then you have to square root it or cube root it or whatever. You need to take the root of that number. If you had multiplied, if you have the multiples, like multiply the whole thing by 2, then you would square the whole thing. You give it the exponent, which means that basically we did a divide coefficient by 2 square root. Okay, so you have to divide the whole thing by 1. So, or square root the whole thing. Okay, 1. Square root, just like that. Okay, so is that an option? And another way of writing that is 1 over k1. Whenever you do a cube root or square root, it's to the 1/2. That's the square root. If it's cube root, it's 1 over 3, etc. And so my guess is that that is the answer, which would be C. So let's take a look. I haven't looked at the key yet. There it is. Okay, 45. I'm just a little too far. And what does it say? 45. Yes, the correct answer is C. So it did the same thing. It's reverse divided by 2. So if you reverse a reaction, it's inverted. So you take that K and you divide it by, what's 1 over K? That's the inversion. And then for square root, you have to the 1/2 power. If it was cube root, to the 1/3 power. So that's the square root of the whole thing in this particular situation. Good. So that is that question. Excellent. So please be sure to ask more questions. But yeah, this is good. Okay. So let's look at so big idea 1. And looking at big idea 1, let me go back to the bamboo paper. Okay. And we'll get a new paper on this one. So big idea 1. All right, big idea 1 is really talking about, well, let me just read it to you. The chemical elements are fundamental building materials of matter, and all matter can be understood in terms of arrangement of atoms. These atoms retain their identity in chemical reactions. So really, it's nice because big idea 1 is all about starting with the atoms and going from there. Some of it's really simple. For example, knowing, like we said before, that the ratio of the masses is always the same, right? So if you have H2O, it's always going to be H2O. This is also the unit where, and I think you guys are fine on the atom itself, but that sometimes there's questions in regards to the electromagnetic spectrum. And I think there were some people that weren't sure about this. Magnetic spectrum. And so you have at one end, you have long wavelengths, okay? And this is gonna all tie in a second. Long wavelengths. So this is like your AM radio, right? So this is like long wavelengths. And then it goes to the short end, and you're looking at some of the shortest ones we have are gamma rays. And so what happens is it gets, you know, and they get really short. I don't know if I can do that. So And gamma, so the long wavelengths, the AM radio, so you have short over here. So short wavelengths, long wavelengths. This is low energy, right? There's AM wavelengths going everywhere. And this is high energy on this side, okay? And then in the middle somewhere is the visible spectrum. And so we might say, hey, right there is the visible spectrum. And you're looking at the Roy G. Biv. And this basically starts with the longest on this end to the shortest on this end. So if this is red, then infrared, they call it IR, infrared's on that side. And this one, if you're going to the short, you get ultraviolet, right? So you get a little bit better idea about this. And then the equations that you'll have to use. So for example, we talked about energy. Energy is equal to H times this. Okay, so we have is basically Planck's constant times nu, and nu is the frequency. So Planck's constant which is equal to 6 point, I get this wrong all the time, 6.63 times 10 to the negative 34th joule seconds, okay? And then the nu, that's frequency. Okay, and that's the units for that is always 1/seconds. So if you can imagine, you've got joules times seconds for H, for Planck's constant, times 1/seconds for nu, which is frequency. The seconds cancel out, you're left with joules for energy. Totally makes sense, okay? And then that right there can tie into the speed of light, right? The speed of light is equal to wavelength times frequency, lambda times nu. So lambda is equal to wavelength, which those units are usually, they're off. You know what? Let me just take that back. I'm saying nanometers. That is the unit. Let's just say that. It's nanometers a lot, except for that c is the speed of light, right? And that's equal to 3.0 times 10 to the 8th meters per second. So here we have a disconnect. We have an issue right there. In fact, I'm going to change the colors on that. Most oftentimes the units for this are in nanometers, but the speed of light is in meters. So you're going to have to do some conversions there. And 1 meter equals 1 times 10 to the 9th nanometers. So hopefully that gives you an idea. We already covered nu, that's 1/second. So basically, right, we've got meters per second, and that's meters times 1/second, which is equal to meters per second. Now, if you rearrange this, nu is equal to c over lambda, okay? And E is equal to H times nu. So you can substitute that and you get E is equal to Planck's constant times C over lambda. So, and these are constants. Just make them orange just for fun. The H and the C are constants. So really, wavelength here is determining the amount of energy. So you could do some calculations with that. That's a possibility. And I see that Arya has another question. So Arya, you have a question on number 58. I believe it's the same one probably. So I'm going to go to the next page. And we'll change this back to this color. So we go to number 58. Practice test number 2. Okay. I'm going to find that again. So sample practice test number to number 58. Okay. So the question is, which of the following carbon-oxygen species has the longest average CO bond length? So CO bond length, and you want to know which one's the longest. Okay. And for A, you have CO. For B, you have CO2. For C, you have CH3CO2 minus. And for D, you have CO3 2 minus. Okay, so looking at this, you have CO. And in a situation like this, carbon monoxide, kind of an interesting one. Your carbon cannot form more than 4 bonds. Your oxygen cannot form more than 2 bonds. So you know that the carbon has at least a double bond here. Okay. Well, you know, I say a double bond. It might take more than that. Well, suffice it to say, you could have something like, well, we'll just leave it like this. So it's a CO. So you have at least a double bond. Okay. Which, you know, is not a particularly long bond, pretty short. CO2, C double bond O on one side, double bond O on the other. So you got double bonds going on both sides, okay? CH3, so C has 3 H's here. It goes to a C, which is going to a double bond here, another O here, and it's just 1 minus, right? Yeah. Okay, so you've got a double bond here, and you have a single bond here, okay? And then you have CO3, 2 minus, so you've got C, double bond O, single bond O, okay? And then there's minuses here and here. Now, here's the interesting thing. You start to get into a resonance structure, all right? So here's my question then. Let's look at C. Is the double bond to this O, or is the double bond, oops. Let's use a different color actually too. Let's use green. So is the single bond here, the single bond here? Where is it? Right here, double bond. You have a double bond here, a single bond and a single bond. Where are they? Where are those bonds? How do you determine where they are? Now, I hope some of you are saying, oh, wait, I remember this now. There are resonance structures, okay? So we have a resonance structure. So if there is a resonance structure, it's not in one location. It's actually in all 3 locations. So I have a C here. So, and you could, if you had a modicum of ability more than what I have, you could easily do this. And then dot, 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 dot. Okay. So what you have here is you have a double bond spread out over 3 bonds. Okay. There's just 1 double bond spread out over 3 bonds. All right. So really, it's definitely not as long as a single bond. If you remember, and just for fun, we're going to make this yet a different color. Single bonds are longer than double bonds, are much longer than triple bonds. Okay. So we have right here, we have a double bond split between 2 bonds, right? And so really what that comes down to is there are 3 bonds between 2 locations. That's like 3 halves, okay? This has 2 bonds over, well, actually, if you want to say it's like 1, 2, 3, 4 bonds over 2 locations. 4 bonds over 2 locations, that's like equal to 2, right? This is like equal to 1.5. Okay. This is, it's by the line, but 2 bonds over 1 location, 2 bonds over 1 location is equal to 2. And then right here, you have 1, 2, 3, 4 bonds over 3 locations. So you have 4 over 3, which is equal to 1.333, okay? So I'm gonna go to the next page just for a second. So what that means is that for A, the bond order is equal to 2. Actually, I think it's like equal to 3, but let's just skip that for a second. B, the bond order is equal to 2. C, the bond order is equal to 1.5. And D, the bond order is equal to 1.33, okay? And the closer to 1, 1 is longer than 2 is longer than 3, okay? So which one has the longest? Well, I would say that D has the longest bonds because it has resonance structures spread out over more bond locations, okay? So let's see what it has to say about that. All right, and we are on 58. 58. Okay, D. CO, also, it has a triple bond. Nah, I didn't do that right. My bad. So I thought it had a triple bond maybe, but I didn't write it that way. So obviously that was wrong. But anyways, so the first A has a triple bond, so it's the shortest. CO2 has 2 double bonds, making that average bond length a double bond, right? So it's a little bit longer than a triple bond. Then in C, you've got resonance forms with 1 double bond and 1 single bond, giving it the average bond order of 1.5. And selection D has 3 resonance forms. And so each one has a double bond and 2 single bonds. So that's 1.3. So D makes it the longest. So hopefully that helped you there. Come back to that. All right. Let's go back to our papers. Real big idea. Okay. Okay, so we're in the first one. All right. Okay, so we're talking about the energy. Got it. All right, so you might have to deal with that. And of course, wouldn't you know, as I'm thinking about this right now, I don't know if those, I wonder if there's the reference sheets. Are they in here? Oh, phooey. I don't know where the reference sheets are. And of course, I don't have anything right handy. Oh, wait, I do have something. No, I don't have something. I've got some reference sheets, but not the reference sheets on the test. Let's just assume that if you have it, you should know the speed of light and you should know Planck's constant, and then you can work with that. This is also a good time to mention, because they talk about, quite frequently, they talk about Coulomb's law. Is that C-O-U-L-O-M-B, Coulomb's law. Now, there's no calculations that you're going to have to do with this, but F equals force times Q1, Q2 over R. Now, I didn't look it up, but I understand what Dominic was saying about there's like a K involved there, but this is, in AP Chemistry, we don't have that. So you're just looking at Q1 and Q2 being the 2 particles with charges. And those particles with charges could be protons or electrons. Q can be particles with charges. So I'll write that down. So really, you're not doing the calculations. That's not going to happen. They're not going to ask you for the force. They're just going to ask you, what's the relationship? So your only 2 options for this are protons or electrons, because those are the only ones with charges. Neutrons, of course, have no charges. And R is, of course, the distance separating them. Oh my goodness, what happened? Between particles, distance between the particles. Okay. All right, so we'll just call those the essentials of that. This would also be the unit where we would talk about electron configuration. And honestly, oops, this is something you guys should know already. Electron configuration. Interestingly enough, some of the students came back from UCLA, and the way that they did the electron configuration was different, which is fine. It's just funny because the professor said something along the lines of, "Remember what you learned in AP Chem? Well, forget that. We're gonna fix all of that right now." Excuse me, which I think is funny. So just briefly though, you have S, P, D, and F. And let's pick something out just for fun. Let's say that you had to do the, you have to do the electron configuration for something like antimony, Sb, okay? And its atomic number is 51. And so that means that that's the number of protons, equals the number of protons. But if it's a neutral atom, that may also be equal to the number of electrons. And so if you're just asked for the electron configuration, which again, very unlikely, but if we did, you need to write that out. Now I'm going to skip over the whole thing and just say, let's go straight to the noble gas configuration. The noble gas that is the row above. So let's, hey, do I still have my periodic table? That's still up. Yes, it is. Hey, that's awesome. Antimony's right here, 51. So we take the noble gas from the row above, which is krypton, and we put it in brackets. And then we start at the beginning of the next row. So that means krypton in brackets. And then this number of row is the, let's see, 1, 2, 3, 4, 5, fifth row. So 5s2. And then remember that you drop an energy level when you go to the d orbitals, which is right here. So you drop one, if this is fifth row, then it would be 4d, back up to 5, 5p, 1, 2, 3. If, let's say, we had done bismuth, you would have had xenon in brackets, you'd have 6s2, you would have had to go to 4f14, 5d10, back up to 6p, 1, 2, 3. Okay, so just the essentials of electron configuration. Oh no, actually, let me back up for just a second. Always fun is, you know what, actually, I'm gonna leave it on that one for a second. Okay. So if you remember, we're talking about electron configuration, that sometimes when you have the argon, so argon, let's say it's the noble gas configuration, argon has the same configuration as an ion. If we have Cl minus, right? Cl minus, you have chlorine, so you have an electron configuration for chlorine. But if you Cl minus, you have an ion, an anion, you've added an electron. It now has the same configuration as argon, which means that it's isoelectronic. So they have the same electron configuration. The same thing with K plus. So you have your electron configuration and you have 4s1. But if it's K plus, you get rid of that electron and now it has the same number of electrons as argon. So it would have the same electron configuration. It would be isoelectronic. All right. So trying to remember the actual ions and what you would do with the electron configuration. Most of the time when it's an ion, especially these halogens, looking at the alkali or alkaline earth metals, if we do an ion for one of those, the electron configuration is a noble gas configuration because that's what it went to. However, we get to have a slight problem if we start using any of the transition metals. If you remember with the transition metals, you might have, let's say, manganese plus 5. Well, oh no, I'm sorry, manganese would be plus 7. Well, that could be a noble gas configuration. Let me pick something different. I'm sorry. Let's do scandium 2 plus, something like that. And if you remember, they lose the s orbital first because the s orbital is further away. So you would have, if you did scandium 2 plus, you're going to lose those two electrons first from the s orbital, which is outside. That's 4s. And then you would lose any from the 3d. So remember that you lose s first because it's further away. It's easier to remove electrons that are further away. So anyways, that might come up. I see that we have more questions. Aria, you have some questions, so let's jump to those questions. Aria's first question is, could you explain what hybridization energy is? That's interesting. Usually hybridization is not referred to as energy. So I don't know if there's a specific question on that one, but I will explain some basics of hybridization. So let me just go, it doesn't really matter, I'll just go up a page. Okay. Hybridization. And when we have hybridization, if we have a molecule, it has, let's use CH3, okay? And so what's happening is you have a carbon in the center. Oh, I'm sorry, not CH3, CH4. Let me erase that. CH4. Okay. And so carbon has, if you want to do its electron configuration, this could pair really well with that. It's 1s2, okay? Then we go to 2s2. And then if you remember from one of the questions, there's like a 2, it's 2p, 2p, oh my goodness. It's 2p2. So because it's 2 over in the p category. You might say that if we're doing this box notation, you have, here's 1s, here's 2s, and 2p has 1 electron in each of the first 2 orbitals. So what I was saying, I'm sorry, a second ago, was they did a 1s2, 2s2, 2p1, 2p1. And so this is saying, oh, these are the first 2 orbitals, 2p. And so sometimes they might refer to them as like, oh, this is xy, and this is xz. And then if you had another one, it would be yz. Would be the last one if it was like 2p0 to show that there's nothing in there. Okay. So now what's happening is that so this is carbon, and carbon is bonding with hydrogen, which has just 1 electron. Okay. So it's 1s is just 1 electron. And so it wants to pair up. So let's say that we have another hydrogen with its 1s, and we have another hydrogen with its 1s. Here's a hydrogen, and here's another hydrogen with its 1s. Okay, and I'm going to go ahead and make these red for this. What happens is that the outer energy level is the one that does the bonding. Do you guys remember that? When you talk about the valence electrons are made of all the electrons in the s and p. So valence electrons, s and p. Okay, here's s, here's p. So these 4 electrons are used for bonding as well. So if you're bonding, then what you could say is, okay, so this right here, this bonds right here. Okay, and then this, you could say, bonds right there. And this bonds right here. and this bond's right here. So there you have, if you talk about this, right? You're pairing up all of these. And so what we say is hybridization is that you have the different orbitals are hybridizing together to get to the full octet. So if they do this, then carbon has these full, right? The S, if we're talking about the second energy level. And it would have all 6 because it borrowed the electrons and it's sharing them, because this is covalent bonding, but sharing them, and it gets to 8. So 2, 4, 6, 8. And the H's have 2, H2, H has 2, H has 2. So it has 2, so it's stable. And so they use the S and the P orbitals. Now, how many of these orbitals did they use? They used all 3 of the P orbitals, right? Because all 3 of them are filled. This is called sp3, right? It used, also, you could be saying that the S represents the sigma bonds, okay? That's the first energy level. And so, well, I'm going to, because then the rest of them are the pi bonds, but I think that's going to be, I'm going to confuse you with double and single bonds. So just leave it like this. So there are, each one of these bonds is an sp hybridized, okay? Because you are using the S and the P's. So because there are, because the S bond, see this, there's one S and then there's 3 P's. There's an S and then there's a P, there's a P, there's a P, sp3. Okay? And really, the easy way is just to say, hey, how many bonds are on the central atom? So if I said that we have H, C, double bond, why am I forgetting this one? Oh, here we go, like this. This is sp2 because there are just 3 things bonded on the central atom. If it was H, C, 1, 2, 3, N, then it would just be sp because there's just 2 things bonded on the central atom. So hybridization is, that's what hybridization is. Hybridization energy, I'm assuming, is the energy involved with that. I don't know how else to describe that, but I haven't seen any questions involving hybridization energy. So hopefully that answers it, but feel free to ask more questions on that. Okay, so that finishes that question. The next question Arya has is, could you do number 19 on the multiple choice questions, chapter 2? Yes, let me grab that paper off the floor real quick. I believe I found it. Number 19, okay. So I'll try to write this out. Let's see. Okay. Yes, lattice points. We did discuss this actually. I don't mind covering it again, but we did talk about this once. Go to a new page. Okay, so this is, let me change the ink on this. So chapter 2, so we're looking at, I believe this was big idea 2. I think it was. Okay. And it was number 19. And so the question was asking you about, it says, which of the following identifies the species that occupies the lattice points in crystals of xenon and xenon difluoride? So it's looking for lattice points. So lattice points in crystal, crystals of xenon and xenon difluoride. Okay, so when you look at this, I would strongly encourage you to write down the things that you know, okay? We know that this is a nonmetal. We know that this is a noble gas. It's very large, okay? And we'll leave it at that. Xenon difluoride, this is a nonmetal plus a nonmetal, which means that it's covalent. It's a noble gas and a halogen. I'm not sure where to go with that necessarily, but they're all nonmetals, interestingly enough. And lattice points, usually lattice points refer to, when we talk about lattice, we usually are talking about salt crystals. So I'm not sure why they're on that, but and when we're talking about a crystal, we're talking about make it a little red just for fun, that, you know, I cannot draw to save my life. Let's just make them really small. So they could be something like this, okay? Or in the case of xenon difluoride, I think it's kind of linear, but you're essentially looking at something that it might be zigzag type of a situation. Let's see if I can do something with this. Okay, and then I'm going to put in a orange, and there could be some, because this is difluoride, so this is my loose interpretation of that. Okay, so you have different points here. You've got points that are xenon, you have points that are xenon and the fluoride. So let's look at the options. It says some lattice points, some lattice points in each substance contain anions. So A says anions, right? Those are negative. Anions would be your nonmetals, but it's a nonmetal with a charge. Okay, and do we see that? I see covalent. This is all covalent. You get this from ionic. So I don't think that can be possible if we have these covalent bonds, right? These are nonmetals. An anion is a nonmetal, but it's a part of a metal-nonmetal combination that is ionic. Okay, well, so that means A is out. Let's look at B. The lattice points in xenon are occupied by ions, while the lattice points in xenon difluoride are occupied by molecules. All right, well, we could definitely add to this and say that yes, these are molecules and these are atoms. Okay, but B says it's let's go here. B says that the xenon are ions and that the XeF2 are molecules. Okay. So this one is correct. This one, not so much. Ions again. We clearly can't use that one. Okay. C, the lattice points in xenon are occupied by atoms, while the lattice points in xenon difluoride are occupied by molecules. So the xenon equals atoms, and the xenon difluoride is equal to molecules. Well, based upon molecules, based upon our conversation we've had so far, these are both correct. I would say that I'm leaning towards giving C the nod. Let's look what D says. The lattice points in xenon are occupied by cations, while the lattice points in xenon difluoride are occupied by atoms. Wow. Okay, we're back to ions again, cations. Still an ion, definitely not it. And then the xenon difluoride are atoms. And that is simply not true. Clearly not it. So I am going to vote for C. I'm going to take a quick look at my solutions guide, number 19. I don't have it up on there. The correct answer is C. There it is. It says that A could be correct for an ionic solid, but xenon is comprised of atoms, so that's definitely not it. Choices B and D are impossible since xenon is not an ionic solid. So there we go. Hopefully that helps you out. So you didn't even have to necessarily know things about crystals or lattices or anything like that. You just have to be able to recognize that xenon is a non-metal, it's a noble gas, it's atoms, and that xenon difluoride, two non-metals, they come to form a molecule, not an ionic bond. Okay. So make that one done. All right. Let's go back to big idea 2, hybridization. Okay, we've finished electron configuration. All right. Now this is going to play into pretty well with, oh, let me write some things down. So we talked about isoelectronic. Oops, that's not the color I wanted. Isoelectronic. Okay. And what I would say is that this is going to be, so that means that argon is equal to Cl minus is equal to K plus. Okay. And this can play into when we start talking about atomic radii. Okay, because more electrons, like if you have more electrons than protons, you're looking at a larger atom. So if I made a little silly graph here, if my electron number of electrons is greater than my number of protons, we have a large radius. If the number of protons is larger than the number of electrons, we have a small radius. Okay, and so if we were to take these three and put them in order, we would say, okay, argon has the same number of both. Chlorine has more electrons than protons, and potassium has more protons than electrons. So that means if we're putting them from smallest to largest, then the smallest would have to be K plus, and the largest would have to be Cl minus, and argon being even numbers right in the middle. Okay, so that would be using that with atomic radii, and that's one of the trends as well. And I think you guys can be able to do the trend of atomic radii. That one's a pretty simple one, but that's how it ties in there with isoelectronics. And let's go to a different page to finish this off. Okay, so now since we're continuing our talk of trends, we can talk with my personal favorite, which is ionization energy. Oops, my Y got a little crazy there. Ionization energy. And that's the energy required to remove an electron from a gaseous atom, or to remove a mole of electrons from a mole of gaseous atoms. Okay, so an ionization energy, as we've talked about before, there's different ways they could ask that. We talked about it briefly. I don't know if you guys remember, like the Z effective charge, right? That's the effective charge of the nucleus. The charge of those protons can pull on the electrons. And so the higher the number of protons, the greater the pull on the electrons. But as you start adding energy levels, you start getting shielding. And so this is where you need to talk about the important things. If you had to write out your answers, you're talking about effective nuclear charge. Okay, which is this right here that's effective. And the other one would be, of course, shielding. So that an outer layer is shielded from the nucleus by an inner layer. So really large atoms that have many, many energy levels, the outside electrons are easy to remove because they're so shielded from the nucleus. And the smaller ones like fluorine has a really high ionization energy, and actually the highest would be helium because there's nothing shielding it. So that's ionization energy. Then there is electronegativity, which is not spoken of very frequently. Electronegativity is spoken very often, but the idea that it is the ability of an atom to attract an electron. So we talk about it not so much as its trend, but an explanation of why fluorine is the most electronegative, or why does fluorine bond with things, or why is it that when you have hydrogen bonding, it's only fluorine, oxygen, and nitrogen. And that's because those are the most electronegative atoms, and their ability to attract hydrogen is the strongest. However, they do like to talk about electron affinity. Okay, and the thing about electron affinity is that the energy released when a gaseous atom gains one or more electrons. So energy released when atom gains electron. Okay. So you don't have to, it's got the same trend as electronegativity and ionization energy. It's just spoken of a little bit differently. So just think of that. That's the when you form bonds, energy is released. So it's like gaining electrons. So electrons are being added, so energy is released when that happens. And it would be similar to saying it's exothermic. If it's endothermic, or if in this particular instance, you have to add energy to remove an electron. So that's where ionization energy comes in. So we've talked about all the basic trends. So making sure you understand the trends and how to explain them and their involvement. That would be good. All right. Let's see what else. Oh, how am I forgetting this? PES. Totally forgot about PES. Let's see. Let me see something. I thought, oh shoot, AP. I completely forgot about this. I apologize. Oh, I really like Bozeman. Let's see. Let's watch a little bit of his video. That's what we should do. And I'll skip around a little bit if it's not. Let's see if I can do this. Oh no, what happened? So I'm hoping you guys can see this. This is a pretty good video. I would love for you to watch this probably more on your own, I think. I'm kind of hoping he, I was looking for PES. Definitely, he does a great job with all this. Oh, here we go. Okay, so I'm going to stop right there. And you guys can look, it's Boseman, it's Coulomb's law, and you guys can watch that video. Basically, he's going to go through and talk about the photoelectron spectroscopy and the idea that you get more electrons, right, as you start working your way up. Let's see if he does another one later on. Okay, so the energy that is required to remove the electrons obviously increases as you increase the number of protons, right? It goes up and up. I want you to always notice the height of the peak, that the peak for helium is twice the height of the peak for hydrogen. Well, 2 electrons were removed from that first s orbital. And then there was only 1 from that, because there's only 1 electron in that s orbital. So I think that's important to note. All right. That's kind of cool. I like that. All right, let's go back to, so PES, going back and taking a look at that, it's going to be important. I imagine a big deal was made about that early on. There might be 1 or 2 questions. Again, just know the basics of it. You don't have to get into a lot of detail. I do want to take a look. Let's see, what time is it? 9:05. Okay. Let's take a look at, since we're talking about PES, which is the photoelectron spectroscopy, and knowing you know how to read that now. I think that we should take a look at let me just make sure it's a part of this. I believe the mass spectrometry, let me make sure that it's in here. I'm sorry, there was something I had forgotten about, which we don't need to go to right now. Okay, so the oops, I make a mess so quickly. I can see it's so frustrating. Okay, so mass spectrometry is you're looking at let me just compare them. So if you have PES, you have a graph that looks something like this with number of electrons and energy here. and it increases going this way. So it takes more energy to get them right here, and takes less energy to get right here. So you might have something like this. And this might be, as an example, this might be 2s, it's out here. And this should be 3 times as high. This is 2p, lower energy, took less energy to get the p's off than the s's off. Okay. The mass spec. So for that graph, too bad I can't put a ruler on this, right? So what you have here is the mass, and usually this is the different isotopes, because if you remember, well, no, you don't remember, it breaks up the molecules into fragments, and because elements are, when you get their average atomic mass, you get the average atomic mass. It's not just one mass for all atoms. There's usually multiple atoms. And then very similarly to the number of electrons, you have abundance. Now, PES is for just the electrons, whereas the mass spec is for the mass of the whole thing, so to speak. One of the questions on your big idea number 1 had a situation where they said, okay, let's have this line be, or this number be 68 right here. And then we're going to make this number be 70. And then we're going to make this number be 72. And we're going to make 2 lines. We're going to have a line right here, oops, that goes up about this high. And then we're going to have a line here that goes up a little bit higher. And again, it's too bad that I cannot draw. There we go. Okay. So what does that tell you? Well, it tells you that something has a mass of 69 and something has a mass of 71. And there's 2 things involved. Now, they didn't tell you what the element was. And they said that it was, just wanting to know what the average atomic mass is. Okay. So you can ask multiple questions about this. I would say that a really good example for this, well, there's a couple different ways to do this. Let's do this. The first question was, number 1, what's the average atomic mass? Now it's multiple choice. You don't know exactly how much is on here. You know that down here, it's supposed to be 0%, and this is supposed to be 100%. Let's just say way up there, but this isn't 100%, but just as an average, or just as a range. Now there's more 69 than there is 71. If there was the exact same amount of 69 and 71, you could say, oh, it's exactly 70. But there's more 69 than there is 71. So probably your average of these 2, if you average them all together, a little bit of 71, a lot of 69, you're going to end up with a mass somewhere in this range, between 69 and 70, but probably right there. Excuse me. So it's between 69 and 70. And that's one of the options. So maybe they'll ask a question like that. What is more likely is that they would say, this is an example. Actually, one question could be, this is a molecule. These are molecules of chlorine. Okay. And so, in fact, let me rewrite it on the other side. Because really what they would have done is this. They actually might not even told you it was chlorine. They do this. Okay. Here's 70. Here's 68. Here's 71. Halfway down. It's 35. 33. 37. Something like that. Okay. And there was a tall, oh my goodness. You know what? I think I'm expecting too much of myself to be able to draw these lines. Okay, here's 1. The second one, I also noticed that this is not 71, this is supposed to be 72. Okay, and you would have probably maybe you would also, oh, I'm sorry, you would also have, like, say, a line right here, and maybe a line right here, and then there's a line right here, and a line right here. I have no idea. So basically what's happening is this is 34, this is 36, 68, 69, 71, oops, 71, 72, something like that. And they said, okay, what is this? And so you look and you say, okay, I see a 34 and a 36. And these are, mass spec is going to break it down into its smallest atoms first, and then its combination of atoms. So which element has a mass somewhere around 34 and 36? And it looks like chlorine is 35.45. So that's interesting. So maybe what you would have is actually, then you would probably have a, oh my goodness, did it again. You would have a taller line right here, okay? So what that means is that this line right here is chlorine 34. Can't even tell what that is. Chlorine 34. And this is chlorine 36. And this right here, the 68, would be chlorine 34 bonded to chlorine. Oh, I'm so frustrated at the moment. Chlorine 34. So 2 chlorine 34s. This line right here, the 69, would be a chlorine. Maybe it would be a chlorine 34 and a chlorine 35, which, gosh, I guess I would have to have a bunch of those, huh? Something like that. I'm kind of making this up because I'm not doing a fantastic job, but you're getting the idea that you're gonna have to piece together. It'd give you all these things and identify the peaks. So I wish I had a better example. Hey, when in doubt, Google it, right? Let's see if I can look up something real quick. Mass spectrometry, chlorine molecule. I bet there's some much better looking images than what I just did. Oh, speaking of which, there's a great one. Let's pick the one that I did. It looks so much better. You guys will be so impressed. Okay. Check it out. Okay, so much better. So there's 35, and so these are intensities. So chlorine 35 and chlorine 37. Those are the individual atoms. And then up here, you have 2 chlorines. They're both 35. You have a chlorine 35 and a 37, and 2 chlorine 37s. And at this one, exactly 70. That means there's 2 35s. And then the chlorine 35 and 37, so you're getting one. This is 72. And then the 74 is just the 2 chlorines that have 37. So much better. I wonder if I can, you know, it'd be really cool. It'd be really cool to be able to post this. I'm going to test out something. What happens if, can I? I was wondering if I could paste something in there, but what's this one do? Oh, imports files. It doesn't do it. Oh, well. So that's much better. Let's get rid of all this and just go back and look at that thing, because I just do a horrible job of winging it. Okay, so you guys get the idea of mass spec. I want to make sure you guys had that, because there may be on your final or maybe on the actual test. Okay, I would say this. This has been a rather long time, and I'm just doing big idea 1. So I'm a little bit not wanting to go into big idea 2 because it's 9:15. I think I'm going to need to do either more of these. I'm going to have to be more efficient with my time. I haven't done any, I haven't done Google Hangouts like this before, which is too bad. I don't want to do 5 or 6 Google Hangouts though, so I'm going to do it, but I'm going to speed these up for next time. I think I'm trying to hit too much. All right, so the last thing we want to talk about is more along the lines of a lab. There's some learning objectives that talk about the student is able to apply conservation of atoms to the rearrangement of atoms in various processes. The student can design and or interpret data from an experiment that uses gravimetric analysis to determine the concentration of an analyte in solution. And the student can design and or interpret data from an experiment that uses titration to determine the concentration of analyte in solution. That's pretty straightforward. So if you guys remember that gravimetric analysis is basically you are precipitating out and then drying it and massing it. So it's a precipitation reaction, okay? Then you dry it, then you mass it. And so that's kind of where the solubility rules come in, and having to know that the things that are soluble are the ammonium, the nitrates, and the alkali metals. So knowing those at the very least. And then basically you're looking at stoichiometry. So there's some overlap here, but being able to, given the reaction, because you'll probably be asked the reaction, they'll tell you what will precipitate out. And then, how much you're going to get or how much you should be getting of your analyte, what you're analyzing, okay? Then there's titration. And titrations are, when we talk about titrations, most often we're talking about acid bases. But titration can be anything. And in fact, we do a redox titration with the potassium permanganate, the bright purple stuff, and hydrogen peroxide. And so it's really just a matter of a variation on the MAVA equals MBVB, because it's all about the moles. That would be a really good song. Moles of A equals moles of B. The point at which, the end point of the reaction. You get the molarity of both, the volume of both, and usually you get 3 of these, and 1 is what you can't find. So you just manipulate the equation to solve for what you don't have. So their endpoints are light pink, or your endpoint was orange-red, or something along those lines. So that's a lab form in Big Idea 1. All right, it's about 9:20, which means I've been going for about an hour and 20 minutes. Big Idea 1 and answering questions. And I was going to do Big Idea 1, Big Idea 2, and some of Big Idea 3. Obviously, this fell far short. So what I'm going to do is, I think we're scheduled for another one later on, but I think tomorrow in class we need to pick another day or something. And I'm going to move a little bit quicker. Maybe I'll try to spend more time planning. And I'm going to list out some questions, and I'm just going to answer those questions. Whatever questions you guys have, come first. So answer your questions, but I'm only going to hit the questions that I list out. I'm not going to keep, because I digress and I move on to other random things. Just do those and then we'll be done. Tomorrow, we're going to do Big Idea 3 and probably 3, 4. And I have some more worksheets. I believe we're starting the testing schedule. I think that's right. So that means that we're going to have about 90 minutes in class. We have more time, which is good. So you guys can work on Big Idea 3, 4, and I would encourage you to work on the sample examination 2, the practice exam. No, I'm sorry, you're working that on your own. Maybe you've already taken the test and you need to do the corrections. So we'll talk about that tomorrow. Anyhow, I hope you guys get some rest tonight. I'm going to get some rest tonight, and I will see you bright and early. Again, if you have questions, please feel free to show up early. All right, guys, take it easy. All right. Bye.